Yeah, welcome. Thank you very much for the opportunity to speak. What I'm going to talk about today is mostly joint work with Alexander Kasprzyk, Giuseppe Pitton, and Ketil Tveiten, and then at the end there'll be some applications of this work, which are joint work with Liana Heuberger, Al Kasprzyk, and Giuseppe Pitton. Right. So the context for what I'm going to say is recent work on the classification of Fano varieties. And just to sort of sketch the background, what's a Fano variety? It's an algebraic variety where the anti-canonical bundle is ample. So this is a positive curvature condition. If you think about the classification of Riemann surfaces, then a Riemann surface is either genus 0, it's the Riemann sphere, or genus 1, the elliptic curve, and or genus 2 and higher. And the genus 0 curves are positively curved. They have the round metric. They're Fano. Elliptic curves are flat, and genus 2 and higher of general type. So Fano varieties are positively curved in that sense. And I guess the most basic examples are projective space, or more generally, weighted projective space. And I guess we're interested in classifying Fano varieties because they're basic building blocks for algebraic geometry. They are basic in the sense of the minimal model program. So in terms of the birational classification of algebraic varieties, and also pretty much every, well, almost all explicit constructions in algebraic geometry tend to start with a Fano variety, start with projective space and impose some equations or whatever. So they're kind of basic building blocks in that sense too. And something to point out is that it does make sense to classify them. So by results of Kalam, and Mori, and Berkar in much greater generality, we know that there are finitely many Fano varieties up to deformation in each dimension. Okay, sorry, you need to bound the complexity of the singularities that can occur. But once you've done that, so for example, for smooth Fano varieties, there are finitely many Fano varieties in each dimension up to deformation. That's Kalam, Kamori. And if you bound how bad singularities can be, that's true for singular Fano varieties too. Okay, so what is known? Well, there's exactly one-dimensional Fano variety, that's the Riemann sphere. 10 deformation families of two-dimensional Fano varieties, those are the Del Pezzo surfaces. And in dimension 3, by this kind of amazing work of Mori and Mukai, we know that there are 105 deformation families of smooth three-dimensional Fano manifold. Sorry, three-dimensional Fano variety. And beyond that, we know very little. So we don't really have a good understanding, even a sketch of the classification of higher dimensional smooth varieties. And if you relax the condition of being smooth, then we don't really know what's going on even in dimension 2. So there's lots to learn. Okay, so far, people could make smiley faces in the chat if that's. Okay, so and I guess a recent idea which grew out of work of Golishev and out of the work of Alessio Corti and his group at Imperial, is that there should be is that mirror symmetry gives you a close correspondence, a close connection between Fano manifolds on the one hand and Laurent polynomials on the other hand. So in a precise sense that we'll describe in a moment, Fano manifolds correspond conjecturally under mirror symmetry to Laurent polynomials. And this has been quite a productive line of investigation, but it really leaves a kind of large question, or raises a large question, which is, okay, so what class of Laurent polynomials correspond to Fano manifolds? Or more generally, what class of Laurent polynomials correspond to Fano varieties with certain singularities under mirror symmetry? And I guess the goal of the talk today is to give you a conjectural answer to this question. So, and something that I want to highlight is that this conjectural answer works in all dimensions. So that's a sort of improvement on the situation we had before. And I want to give some evidence for this conjecture. Okay, so let me say a little bit more about the correspondence between Fano varieties and Laurent polynomials. So if you give me a Fano manifold, or more generally, if you give me a Fano orbifold, a Fano variety with q factorial singularities, then I can form what's called the quantum period, which is a generating function for certain Gromov-Witten invariants of your Fano variety X. And so it's a power series in one variable t, and the coefficient of t to the d is this Gromov-Witten invariant that I've written here. The precise details are not going to be important in what follows, but if you're familiar with the theory, then it's a genus 0 Gromov-Witten invariant in degree d with one insertion, and the insertion is a volume form, and the d minus 2th power, the appropriate power of the universal cotangent line class. So if you're thinking about this in terms of enumerative geometry, this number is a virtual count of degree d curves in X constrained to pass through a particular point, particular generically chosen point, and with a fixed complex structure. So you give me a Fano manifold, I'm going to give you back this power series, this generating function for Gromov-Witten invariants. And sort of in the theory of mirror symmetry, this quantum period plays an important role. So it's a solution to the quantum differential equations for X. So if you take this generating function and you find the differential equations that it satisfies, those encode the quantum cohomology or part of the quantum cohomology of X. So this is the identity component of Giventhals' J function. That is another way of saying it. Okay, so that's the object on one side of mirror symmetry, counts of curves in Fano varieties. On the other side, I've got a Laurent polynomial in n variables, where n is going to be the dimension of my Fano. And if you give me a Laurent polynomial, I can define the classical period. So you give me f, and I'm going to write down a function of one complex parameter t as follows. I take 1 on 1 minus tf, and I integrate it against dx1 on x1, dx2 on x2, blah, 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 dxn on xn, and I integrate it around the unit circle n times, and I divide by 2 pi I to the n. And that's an analytic function of this variable t. Can we imagine for a moment that t is really, really small? So then you could take this 1 over 1 minus tf, and you could expand it as a geometric series. So you'd have like 1 plus t times f plus t squared times f squared plus t cubed times f cubed, and so on. And then you can do this integral by Cauchy's theorem. If I'm integrating around the unit circle, I'm picking up the residue at 0, right? Which, if you work it out, means that what you're doing is you're taking the coefficient of under t to the n is the constant term in the Laurent polynomial, which is the nth power of f. Okay, so what did we do? We took this Laurent polynomial, we made the classical period, which is this analytic function. If you expand it as a power series, you can find out what the coefficients of that power series are. But also, by general theory, this classical period satisfies a bunch of differential equations called the Picard-Fuchs equations. So I guess, f is a Laurent polynomial, right? So it's a map from C star to the n to C. So you can think of that as a fibration away from the singular, away from the critical values. And the Picard-Fuchs equations associated with that vibration, they annihilate the classical period. Okay, so far. Smiles or frowns. Cool. Okay, so what does mirror symmetry mean for us? Well, we have the quantum period. I'm just going to flick back a page, 1 second. The quantum period was this generating function, 1 plus the sum of c dt to the d. So what I'm going to do now is I'm going to regularize it by chucking a d factorial in there. This is taking the inverse Fourier Laplace transform. Okay, so now we're going to make the regularized quantum period. And what does it mean for a Fano manifold X to correspond under mirror symmetry to a Laurent polynomial F? Well, for us, it precisely means that the regularized quantum period of X is equal to the classical period of F. In other words, if you take the regularized quantum differential equations, the ones that you get by taking the Fourier transform, then they coincide with the Picard-Fuchs equations for the mirror Laurent polynomial. Okay, so can I make a sort of aside for the future? So suppose you're sitting in the audience and you know what a cluster variety is. Then you might be sitting there thinking, Tom, this is hopelessly naive. The mirror partner to a Fano manifold is supposed to be a cluster variety. It's supposed to be a variety together with a function on it and a bunch of nice charts on that on that cluster variety. And I guess what I'm saying, what this sort of more down to earth point of view is saying is that, okay, instead of thinking of the mirror to a Fano variety as a cluster variety, I should take a particular chart on that cluster variety, whereupon I get a copy of C star to the n. So that's where where the variables of my Laurent polynomial live, and I get a Laurent polynomial, which is f. And so maybe the point of this point of this talk is that you can get quite a long way by taking the Laurent polynomials that arise like this seriously as Laurent polynomials. Okay, so just to sort of recap, if you give me a Fano manifold, then being mirror to a Laurent polynomial means the regularized quantum period of the Fano manifold coincides with the classical period of the Laurent polynomial. And then we won't go into this, but we're quite good at computing Genus-zero Gromov-Witten invariants by now. So sort of Given-Tiles mirror theorems for toric complete intersections and things like another kind of related work give you Laurent polynomial mirrors for a large number of Fano varieties. If you give me a Fano variety constructed in some way, I'm probably going to be able to find you a Laurent polynomial that is mirror to it. But the question is maybe whether you can go the other way. Can you, starting from a Laurent polynomial or starting from a classification of Laurent polynomials, deduce the classification of Fano varieties? An important point, an important thing, is that the correspondence between Fano manifolds and Laurent polynomials is not one-to-one. It's not one-to-one on the Fano side because we're thinking about Fano manifolds up to deformation. Gromov-Witten invariants are deformation invariants, so the quantum period is an invariant of the deformation family, not of the Fano variety itself. And on the other side, we're thinking about Laurent polynomials, and we're thinking about their classical period, this thing. But there are special changes of variables, the changes of variables of a special form, which preserve the classical period. So, for example, if you just make a monomial change of variables, right, xi x1 is replaced by x1 to some power, x2 to some power, and so on. And if you choose those powers so that the resulting matrix is in GLNZ, so that's a monomial change of variables, then this integral is not going to change by the change of variable formula. But f, the Laurent polynomial, is going to change. So I definitely, a Fano variety is not mirror to a unique Laurent polynomial. If it has one mirror, it has infinitely many. But more seriously, here's a different sort of change of variables which also preserves the classical period. So can I take x1 to x1, x2 to x2, and so on, xn minus 1 to xn minus 1, and then I'm just going to mess with xn. So I'm going to replace xn by some Laurent polynomial in the other variables times xn. And now if you go and you apply the change of variable formula to this change of variables, you will discover that the classical period doesn't change. It's essentially because this thing is the multiplicatively invariant differential form. So if you multiply xn by something, it doesn't do anything. Okay, so the composition of these sorts of change of variables are called mutations. And
sorry,
I guess they
yes. Sorry, I can't quite unpack this. Are you just doing changes of coordinates on the torus? Or are you doing something more general?
This one is a change of coordinates on the torus. This one is a birational change of coordinates on the torus because it's not invertible where that person vanishes.
Oh, okay.
So in a minute, I'm going to say it more invariantly. It's going to be much more obvious. Or that's obvious.
But you're restricting. But you're not allowed arbitrary changes of coordinates on the torus. Are you saying?
So no, so I'm going to say in a moment exactly what I mean invariantly, but it's equivalent to allowing compositions of transformations like this and transformations like that. In fact, let me just go forward a page. Can I just say this differently? Okay, so the Laurent polynomial we're thinking about is it's the exponents of the Laurent polynomial live in some lattice n. So the torus that you're thinking about is presumably the dual torus M tensor C star. So here's a change of variables I could do. I can choose a primitive element of the dual lattice, and I can choose a Laurent polynomial which is supported in the kernel of that linear form. And then I can write down a cluster transformation like this. So, I take a rational function on the torus, or a Laurent polynomial or rational function on the torus, and I make this change of variables. Everywhere I see x to the gamma, I replace it by x to the gamma, but multiplied by my Laurent polynomial to the power w of gamma. That's exactly the same thing as we said on the previous page. But that probably makes the fact that this is an automorphism of rational functions on the torus probably makes it clear that it's a birational map on the torus. Can we just take this formula for a minute? So what are its ingredients? An element of the dual lattice, so a kind of choice of direction, and a Laurent polynomial, which is supported in the kernel of that person. So if I go back, a page, it's this. So here here W, my weight vector, is 0, 0, 0, 0, 1, and my factor is this Laurent polynomial. So this is just another way of writing cluster transformations in coordinates. But I guess if you're me, writing it like this helps when you're trying to work out that this is invariant. Okay, so in this context, kind of mutations were introduced by Galkin and Usnich, and then by Akhtar, myself, and Sergei Galkin and Alexander Kasprzyk. And then if you write them like this, and you discover if you write them in this more invariant way, they are cluster transformations that occur in the theory of cluster algebras. So if this Laurent polynomial is a binomial, then these really are the cluster transformations turning up in work of Fomin and Zelevinsky and Fock and Goncharov. More generally, they're what are called LP algebras, or Laurent phenomenon transformations, studied by Lam and Pilayevsky. And then in this context, in the context of mirror symmetry, these are exactly the wall-crossing transformations that come up in the work of Gross and Siebert and Gross, Hacking, and Keel. So, going back to Ed's question for a moment, are these transformations of the torus? Yes, they're birational transformations of the torus, which means that if you take a Laurent polynomial and you apply a mutation, then in general, you will only get a rational function. You will not always get a Laurent polynomial. Can we just do an example? So can we think about this Laurent polynomial? So this one here, y plus 1 on xy plus a on y, where a is a constant, plus x on y. So I'm going to draw the Newton polytope of this Laurent polynomial. So I'm going to so that's the convex hull of the exponents that occur. So the exponents here are, this is x to the 0, y to the 1. So there's the point 0, 1. This is x to the -1, y to the -1. So there's the point -1, -1. This is the point 0, -1. That's the point 1, -1. And I take the convex hull and I get its Newton polytope, which is this triangle over here. Okay. And then, so I guess I can notate the Laurent polynomial itself by writing coefficients on the lattice points in the Newton polytope. So, you know, this A is this A, this 1 is this 1, and so on. And let's try and make the mutation which sends x to x and y to quantity 1 plus x times y. That's a perfectly legitimate mutation from the discussion earlier. And f, which has this form, it's y plus quantity 1 plus ax squared divided by xy. So if you apply the mutation, you get 1 plus x times y from here. And this fraction becomes this fraction. The xy in the denominator becomes incorrectly. I'm sorry, I've missed a factor of x. Sorry. So the xy in the denominator becomes x times 1 plus x times y. Notice that this is not a Laurent polynomial in general, because this is not a monomial. However, if I choose A correctly, so for certain very special values of A, this is a Laurent polynomial. Well, not certain very special. If A is 2, then, because if A is 2, this is 1 plus 2x plus x squared on the top. So I get, 1 plus x times y plus 1 plus x squared over x times 1 plus x times y, and this cancels. So, in general, the mutation of f is not a Laurent polynomial, but if I have very special choices, so if I'm very lucky with my coefficients, then a mutation will take a Laurent polynomial to a Laurent polynomial. Can I do spooky foreshadowing of the talk? This example illustrates two things, right? It illustrates the fact that being compatible with mutations imposes coefficients, imposes being compatible with mutations imposes conditions on the coefficients of your Laurent polynomial. If I want this Laurent polynomial to be compatible with this mutation, then A has to be 2. Otherwise, the cancellation doesn't happen. Also, if A happens to be 2, this Laurent polynomial is a mirror to P1 cross P1. So being compatible with mutations singles out special Laurent polynomials. Later on, we're going to conjecture that this being compatible with enough mutations singles out the mirrors to Fano varieties. And being compatible with mutations kind of tells you what the coefficients of your Laurent polynomial have to be. Okay, happy so far?
Can I maybe quickly ask a very naive question? So you're looking at these mutations, but is it clear? I mean, of course, they're very interesting and have very nice structure, but why? I mean, I could imagine there are other birational automorphisms mapping Laurent polynomial to Laurent polynomials. So why exactly the mutation?
So okay, so from my point of view, I don't know. Is Anne-Sophie in the audience? I think she is. Anne-Sophie, do you want to come in here? There is some idea that if I have...
Yeah.
So something like, if I have a birational transformation of the torus with, and then I'm going to be unable to say the right words, but then it's expected to be a composition of these things. Isn't that right?
Yeah, so a volume preserving birational transformation plus some additional condition for a composition of mutations, which we haven't yet entirely identified. In dimension 3, it shouldn't be a problem.
I see. So I would generate the algebra of all these mutations, and that are all the ones which should preserve these integrals.
Yeah, exactly. Yeah. So and something like that is expected to be true in general, or hoped to be true in general.
Yeah.
Okay. Cheers.
Cool. All right. So if we go back to our kind of maybe goal for today, how can we characterize those Laurent polynomials which arise as mirrors to Fano manifolds? And let me just give some sort of historical discussion. Okay, so the first kind of systematic observation along these lines was by Galkin and Minkowski. So their observation was you do really well by putting binomial coefficients on the edges of your Newton polytopes or Newton polygons. So if we just go back a little bit, I mentioned that if A equals 2 here, then that gives you a mirror to P1 cross P1. So then I'd have 1, 2, 1 along that edge. And in general, sort of putting binomial coefficients along the edges of at least Newton polygons seems to do quite well. So as you may know, there are, if you think about reflexive polygons, then there are 16 reflexive polygons up to GL2 equivalents. And if you put binomial coefficients along the edges of these guys, that gives you 16 Laurent polynomials. Actually, some of them are mutation equivalent to each other. So you end up with only 8 mutation families. And those do give you mirror partners to 8 of the 10 Del Pezzo surfaces. So this is kind of the first idea of a recipe. And for what it's worth, the 2 missing Del Pezzo surfaces here are dp1 and dp2. And these are the Del Pezzo surfaces where minus kx is ample, but not very ample. And why is this relevant? So something that I'm hiding here is if X is Fano and it's mirror to a Laurent polynomial F, then there's expected to be a geometric relationship between X and F, which let me just explain. So F, you can form the Newton, take the Newton polytope of F, and then you can take the spanning fan of P. So you can take the fan just spanned by the faces of P, and then that gives you a toric variety, which I'm going to write as XF. I should probably write it as XP because it doesn't actually depend on the Laurent polynomial or itself, it only depends on its Newton polytope. But the expectation is that if X is Fano and it's mirror to F, then there's a degeneration with general fiber X and special fiber XF. So there's supposed to be a QG deformation where the general fiber is your Fano and the special fiber is this generally singular toric variety. Why is this? So what does that have to do with Del Pezzo surfaces? Well, given that we were only thinking about reflexive polygons, then and given that the anticanonical bundle is preserved inside these degenerations, I'm only ever going, if I'm using reflexive polygons, I'm only ever going to be able to see Fano varieties where minus kx is very ample because the toric varieties ample and very ample are the same. So, okay, so that was an aside, but the sort of general point was, right, what could you do? You could put binomial coefficients on the edges of your polygon or polytope, and that scores you the Del Pezzo surfaces, most of them. Okay. It does not work brilliantly in 3 dimensions. So there are 4,319 reflexive polytopes. You could apply this ansatz. This gives you 4,319 Laurent polynomials. You do find mirrors to 92 of the 105 smooth Fano threefolds. That's pretty good. But you also find 2,000 things which are nothing to do with anything. So probably this approach needs some refinement. And a sort of a more effective attempt in 3 dimensions was this idea of Minkowski polynomials, which was introduced in, I guess, joint work with Korti and Galkin and Golishev and Kasprzyk, and studied in this paper with Akhtar and Galkin and Kasprzyk. So the idea being that if you give me a 3-dimensional reflexive polytope, I can try to build a mirror Laurent polynomial with that Newton polytope, which is mirror to a Fano threefold, and I do it by looking at Minkowski factorizations of the facets of that polytope. If you're familiar with the work of Klaus Altmann about deformations of toric singularities, deformations of toric singularities are controlled by Minkowski factorizations of Newton polytopes. So that, yeah, this feels like it might be in some sense correct. Okay, so suppose I give you one of these 3-dimensional reflexive polytopes. What do? Well, you look at the facets that occur. So suppose you see a facet like this, and you take its Minkowski factorization. The Minkowski sum, sorry, I should say this, the Minkowski sum of 2 polytopes or polygons or whatever is just the sum little p plus little q, where little p is in P and little q is in Q. So, for example, this person that we see here is the sum of this and this, because if you put this person everywhere in here, then you get this person. Was that clear? Cool. Okay, so what we're going to do is we're going to look at three-dimensional reflexive polytopes. We're going to look at their facets, and we're going to see whether we can Minkowski factorize them into AN triangles, which are triangles where you've got one long edge of length n and two edges that are just of length 1. And if you do have a Minkowski factorizations into AN triangles, then you can put binomial coefficients on the edges of each of your pieces and just multiply out the Laurent polynomial to get the coefficients that you put on each face. So, for example, if I had my factorization like this, then this factor would give me 1 plus xy, which are the lattice points that I see, and this point will give me 1 plus y, which is the lattice points that I see. And if I multiply out those polynomials, I get a polynomial which has this as its Newton polytope, so I know what coefficients to put on the faces, and I always get binomial coefficients on the edges. So this gives me a recipe. Just to be clear, here's an example which I'm going to skip over. Minkowski factorizations into AN triangles may not always exist, and Minkowski factorization isn't unique. So even if the factorization exists, it may not be unique. So you don't always get a unique answer for what coefficients you're supposed to put on a facet. So for example, this thing that looks a bit like a house, the recipe gives you two possibilities, either 2 or 3. So, so the recipe with Minkowski polynomials says, okay, look at all the facets, work out the Minkowski factorizations, work out what could go on each facet, and assemble them in all possible ways. So that gives around 3,800 Laurent polynomials, which fall into 165 mutation families. Now, 98 of those are mirror partners to the smooth Fano threefolds with very ample anticanonical bundle. So, and 67 of those are not mirror to any smooth Fano threefold. So, you know, this is an improvement on the previous situation, but it's still not perfect. And it also has various other drawbacks. It only applies to reflexive polytopes. So there's no possibility of finding the other 7, for example, because there is no degeneration with central fiber. So there's no Q degeneration of any of these 7 with central fiber given by a reflexive polytope. It only applies in dimension 3. And also, if you take a Minkowski polynomial and you mutate it, then in general, you do not get a Minkowski polynomial. So it's not closed under mutation, which given what we saw earlier is maybe we should think of as a defect. It's even not closed under mutation if you know that F and G are both have reflexive Newton polytope. You can find F, which is a Minkowski polynomial, and G, which is not a Minkowski polynomial, which are mutation equivalent. So that's also potentially a problem. Okay, so what I want to describe today is an ansatz which works in any dimension and is free of those drawbacks. So what we're going to do is we're going to start with any Fano polytope. That means the origin is in the strict interior of the polytope and the vertices are primitive. We put 1s on the vertices, insist that the coefficients of at each vertex are 1. Is it clear what I mean by put 1s on the vertices? I'm trying to build a Laurent polynomial with a given Newton polytope, so I'm trying to pick coefficients for every lattice point. So I'm going to pick the vertex coefficients to be 1. I'm going to insist on that. We can come back to this point, but for Golisher, for instance, it seems to be important that the Newton polytope of F is the same mod P for every prime P. So that more or less forces you to have ones on the vertices. And then we're going to insist that F is compatible with as many mutations as possible. And that's, so we're going to, in that sense, construct maximally mutable Laurent polynomials. And an important point here is that we can read off what the possible mutations are from the polytope. That's probably quite plausible. I'm going to go back in my notes for a minute. You know, if we were in here, for example, if you wrote out this mutation in terms of the weight vector and the factor, this would be the factor. This was the thing I was calling H, and the weight vector W would be 0, 1, which is a normal vector to this edge. So it's plausible, and indeed it's true, we prove it, that if you give me just the polytope itself, I can read off what the possible weight vectors are and what the possible Newton polytopes of the factors are. So, you know, just from the combinatorics of the Newton polytope, you can say what the possible mutations are. Okay, so now we play the game that we played before and impose as many compatibility with as many mutations as possible. So if we just consider this example, so here's the origin. This is the polytope that I'm thinking of as the Newton polytope. We've put ones on the vertices. And then we could imagine mutations which are to do with this edge here. So you could imagine taking, you know, my weight vector to be 0, 1 as before. And then you could say, OK, well, why don't I take my factor polynomial to be 1 plus x? And then imposing compatibility with 1 plus x with that mutation will give you a bunch of equations on these on the coefficients of these lattice points. But in fact, because this thing has length 4 and is at height 1, I don't just have to be compatible with 1 plus x. So I could actually be compatible with 1 plus x to the 4. I could actually mutate away a fairly big factor. And when I do that, I discover that that forces binomial coefficients along these edges. And now you keep playing this game and you find some more binomial coefficients. And if you do this example, then you'll discover that actually the system of equations that you get does not uniquely pin down the coefficients. There's a one parameter family of Laurent polynomials which are compatible with all of the mutations that this square permits. And you know, this is what it is. Alpha is the parameter. So if you give me a polytope, I can look for Laurent polynomials with that Newton polytope compatible with a maximal set of mutations. And one of two things will happen. Either that pins down all the coefficients, or it doesn't. There are some free parameters. And if there are no free parameters, so if we're in the first case, we're going to call these rigid maximally mutable Laurent polynomials. A subtle point that I'm not going to emphasize here is that in dimension 3 and higher, in general, your polynomial won't be compatible with all of the mutations that the polytope permits. So from the polytope, you can pick out a set of possible mutations. In general, there is nothing that is compatible with all of those mutations simultaneously, but so you have to pick a kind of maximal subset where these equations have solutions. So, yeah, so we have to say maximally mutable moderately carefully.
Question, Tom?
Go ahead.
So there's obviously some choices involved, right? The kind of ones you allow. So does that lead to lots of possibilities, or is there a nice way to make some choices leading to some best end game?
So can you say the question again, just so I get it clearly into my head.
So you're making some choices, if I understand right, because of the sorts of mutations you're going to allow for a given case. And that could lead to different answers if you make different choices. So is there a preferred way to make those choices? Okay. Or do you get genuinely different possible solutions?
So that's a great question. Can I tell you, let me tell you what we allow. So we allow these sort of cluster style transformations where, I mean, as always, this the factor that we're using has to be perp to the so this is a general cluster transformation has these properties, but we also require that H has ones on the vertices and has coefficients in the natural numbers. So that it's a very interesting question about what, you know, maybe I should relax maybe I should relax this condition, but I don't know what the class of I don't know what is interesting about the class of Laurent polynomials that you would get by doing this. But in any case, we're going to insist that all of our polynomials and all of our factors have ones on the vertices, and when they have fixed coefficients, they have positive integer coefficients. Okay, so I'm going to skip quickly over exactly how to say compatible with a maximal set of mutations precisely. So the reason one has to be slightly careful here is, you know how we had these monomial changes of variables earlier? This kind of, you know, we had this idea that you have a Laurent polynomial, you have its classical period. The classical period is invariant under monomial changes of variables, and it's also invariant under these more complicated changes of variables. And we'd like to think of the monomial changes of variables as kind of being trivial somehow. We'd like to mod out by them. But you need to be slightly careful when you do that, because some Laurent polynomials have automorphisms, have monomial you know, are invariant under certain monomial changes of variables. So you need to keep track of automorphisms properly, otherwise things end up getting tangled up. So precisely what we do is we identify two mutations if they differ not by an arbitrary element of GLN, but by a shear transformation. And then what does it mean for something to be compatible with as many mutations as possible? Well, you build what we call the mutation graph. You start with your Laurent polynomial f, and you look at all possible mutations out of f. So, and each mutation is going to have a direction associated with it, and it's going to have this factor where we're considering the factor only up to multiplication by an appropriate monomial. And so you make a graph where, so you started with f, and then I'm going to add a bunch of vertices, one for each mutation of f, where you label the vertices by the Laurent polynomial g, and you label the edges by the data about the mutation that got you from f to g. And then you keep doing that. You do that again for G, you do it again for all your other mutations. You get a graph where the vertices are labeled by Laurent polynomials and the edges are labeled by mutations up to shear. And then erase the edge labels, turn all your vertex labels, which are currently Laurent polynomials, into their Newton polytopes, and now you've got yourself a graph. We'll call that the mutation graph of f. And if you ever have a Laurent polynomial with variable coefficients and you specialize some of those variables to values, like we did earlier, where we had that Laurent polynomial that depended on A and we specialized A to 2. When you do that, the mutation, you can only ever get more mutations by specializing. But if you specialize coefficients, sometimes you get more mutations. You can't ever get less. So specializing coefficients gives you a bigger mutation graph. There's an injection from your general person into your more special person. And we say that a Laurent polynomial is maximally mutable if its mutation graph is maximal. Okay, that's coming back sort of out of the thickets of detail. That was saying compatible with a maximal set of mutations precisely in a way that doesn't get tangled up by automorphisms of your lattice. Okay, and the upshot of all of this, the result of all of this, is the following conjecture. So we conjecture, this is joint work with Kasprzyk and Giuseppe Pitton and Ketil Tveiten, and really goes back to sort of the key ideas come from work of Kasprzyk and Tveiten at the Pragmatic Conference in 2013, and also conversations with Alessio Corti and Vasily Golyshev. So the conjecture is that rigid maximally mutable Laurent polynomials up to mutation correspond one-to-one with Fano varieties with terminal, locally toric, QG rigid singularities up to deformation. And here, if you've got a Laurent polynomial in n variables, then it corresponds to an n-dimensional Fano variety. So rigid MMLPs correspond to Fano varieties with mild terminal singularities. Okay, why haven't we seen? So a moment ago, we were just talking about smooth Fano threefolds, right? Why wasn't I talking about terminal locally toric QG rigid Fano threefolds? I guess the point is that a moment ago, we were talking about reflexive polytopes. We were talking about Gorenstein varieties. And in dimensions 3 or less, terminal Gorenstein QG rigid implies smooth. So this is actually a generalization of what we were discussing before. And yeah, so this is really the sort of takeaway point for the talk. Mutation families of rigid MMLP correspond one-to-one, we conjecture, to deformation families of terminal Fano variety with mild singularities. Let me just say some very briefly some evidence for this. So in dimension 2, Kasprzyk and Neal and Prince classified all polygons that could possibly admit a rigid maximally mutable Laurent polynomial. And then in our recent paper, we gave a precise characterization of MMLPs in 2 variables. And if you combine those, you discover there are exactly 10 mutation families of rigid MMLP in 2 variables. And those correspond exactly with the smooth Del-Petzos. In dimension 3, we have effective algorithms for finding rigid MMLPs with a given Newton polytope. So we give a computer-assisted classification of rigid MMLPs in dimension 3, where the Newton polytope is reflexive, and we discover exactly 98 mutation families, and those correspond one-to-one with the 98 families of Fano threefolds, smooth Fano threefolds with very ample anti-canonical bundle. And then you could try and find rigid MMLPs without reflexive Newton polytope. And so we go off and we do that, and we find 7 more families that correspond to the smooth Fano varieties. The 7 in the 98 plus 7. And just to finish with, you might want to kind of move kind of beyond the world of reflexive polytopes, So this is joint work in progress with Liana Heuberger and Kasprzyk and Giuseppe Pitton. So okay, so you could, for example, instead of taking reflexive polytopes, you could take three-dimensional canonical polytopes and try to find rigid MMLPs with those Newton polytopes. And when you do that, you find roughly 8,000 mutation families of such rigid MMLP. And these should correspond to three-dimensional Fano varieties with marked singularities. So you could ask, okay, where do these fall in the landscape of Q-Fano threefolds? So you may be familiar with the graded ring database. It's work of Brown and Altenok and Reed and Kasprzyk, which gives possible Hilbert series for Q-Fano threefolds. And from a Hilbert series, you can read off, for example, the codimension of an embedding into projective space. That's what this axis is. Or you could read off the genus of the curve given by the self-intersection of an anti-canonical section. That's what this is. And so this is the kind of distribution of possible Hilbert series of Q-Fano threefolds. This is likely to be an overcount. So there are some Hilbert series here that are not realized by actual varieties, but the Hilbert series of every actual variety should be here. And then you can work out from our maximally mutable Laurent polynomials, you can work out what the Hilbert series of the corresponding variety would be if it exists. And so this here's the corresponding heat map. So the gray shadow here is the shadow of the GRDV data, but this is where the varieties predicted by MMLPs live on the kind of plot of Hilbert series. That's probably a good place to stop. Thank you very much for your time.